Okay, should I have my volume
No, I don't think so. All right, folks. Um, Welcome to day two. Thanks everyone for being here. Um, so we're changing gears just slightly. We're going to be talking about gravitational waves. And this is purposeful, both in terms of there's a lot of scientific synergies, as Teo talked about, between the optical and the gravitational wave case. But in particular, will be demonstrating and we'll get to work on how to manipulate time series and images in some ways together. And so I'm really excited. Again, we're all looking forward to sort of working on the BTS data set for Friday. And so there's multimodal data. And gravitational waves actually provide a lot of really interesting kind of synergies between the types of data we have. And so Will's here. He's my graduate student. Welcome, Will. Thanks for being here. And yeah, here we go.
Okay, yeah. So, right, as Michael said, I'm going to be talking about gravitational wave detection and in particular how we can do that with machine learning. This is a slide I like to put at all the starts of my gravitational wave talks. It covers just about everything that needs to be said. Gravitational waves are these large-scale astrophysical events that cause ripples in space-time, and we detect them with ground-based interferometers. We have LIGO Hanford, we have LIGO Livingston, we have some others around the globe. But let's kind of go into what that actually means. What are gravitational waves? Where do they come from? What do they look like? Gravitational waves are a result of general relativity, and they are oscillations in the metric of space-time. Essentially, what that means is that they will compress space in one direction and stretch it in the perpendicular direction, and then vice versa, compressing and stretching over the course of one period of oscillation. Just like electromagnetic waves, gravitational waves have two polarizations. So with electromagnetic waves, you have vertical and horizontal polarizations. With gravitational waves, you have these two plus and cross polarizations. You have these two modes of oscillation that occur. It's not super important to understand where these come from, just that they exist, and they'll come up as we go through the notebook and through this presentation a little bit. They're a result of this nice wave equation that we get from general relativity. And the distortion of an object is described by what we call the strain H, which is the change in the length of an object divided by the length of that object. So it's a dimensionless quantity. Far away from the source of the gravitational waves, the strain is given by this, roughly, approximately. The details don't really matter there. The I is the quadrupole moment. But what's really important is this prefactor, this G over C to the 4, which works out to about 10 to the negative 44 meters per joule. So gravitational waves are very, very weak in the units that we normally work with, and they get weaker with distance because of this 1 over R factor, which makes them hard to detect, and we'll come back to that a little bit. Where do gravitational waves come from? Realistically, any asymmetric accelerating matter. So if I wave my arm, and a gravitational wave there, probably. I don't know. But realistically, we need high density, high acceleration, or ideally both to get a large quadrupole moment, which makes black hole or neutron star mergers ideal because those are both very dense objects and they accelerate rapidly into each other as they merge. What do they look like? Well, it's not the same for every source of gravitational wave, but for at least compact binary signals, this is the general form. I've plotted here one of the polarizations of these waveform for a binary black hole and for a binary neutron star to give you a sense of what they look like. The structure is similar, but you can see that the binary neutron star signal is longer and quieter. And in theory, there are some effects of the fact that the continuum of mass in a neutron star. So as the neutron stars fall into each other, they get ripped apart, and that affects the form of the wave. But that's a higher order effect to the wave. A couple of things to note is we have that the derivative of the frequency with respect to time, it goes as the frequency to the 11th third, which means that the frequency increases over time. We also have that the time to merger is inversely proportional sort of to the mass of the system, which means that heavier systems merge faster, which is what you can see here. Okay, great. How do we detect gravitational waves? We use these advanced interferometers. We have a network of them around the globe. We have two LIGO interferometers. We have one in Hanford. We have one in Livingston. We have the Virgo interferometer in Italy. We have the Kagra interferometer in Japan. We have LIGO India, which is under construction, and we're soon to have, well, soon, in the course of years, we'll have the space-based LISA interferometer. As the gravitational waves pass through each arm, they cause each arm of this L to shift by a different amount, and that interference pattern can be picked up by the sensors there. So to give kind of a schematic of what that looks like, here we have a diagram, basic diagram of what the interferometers look like. As the laser comes through and goes to the beam splitter, it passes through each arm and reflects off a mirror at the other end. As the gravitational wave passes through each arm will lengthen or shorten. And then as the laser comes back and recombines and goes to the photodetector, the interference between the waves will cause a different pattern of brightness and darkness. When the waves are in phase, you'll get light. When the waves are out of phase, you'll get nothing. What kind of data do we get out of these detectors? Well, and forgive the image. I don't know why it looks older than the internet, but it looks like this when I found it. We get a continuous set of time series data at various sampling frequencies, some 1 hertz, some at 128 hertz, or some like our gravitational wave data at 16 kilohertz. Oops. So we have the gravitational wave signal channel. We have physical environment monitors, seismometers, accelerometers, magnetometers, etc., that pick up on various sources of noise that may be present, that may be interfering with our gravitational wave signal. And we have internal engineering monitors that monitor the status of different pieces of equipment within the detector. All these together produce about 2 terabytes of data per day. So we have a lot of data to work with, which is great for doing machine learning because the more data, the better. The more data we can show machine learning networks, the better we expect them to be able to do. I'm going to ignore all of these other channels of data, even though they are very important for work in removing noise from the gravitational wave strain channel, and just focus on the gravitational wave channel for this lecture and for the demo that we're doing today. Within the gravitational wave channel, there is noise. We have a lot of sources of noise. We have just fundamental noise in the detector. We have environmental noise from earthquakes or tides or what have you. We have technical noise from the operation of the interferometer. And the noise is typically louder for than the signals themselves, which makes it a challenge to detect anything. The noise we characterize by this power spectral density, this PSD, which is essentially the power of the noise as a function of frequency. So you can see that there's a lot of noise power at lower frequencies between 10 and say, I don't know, 50 hertz. And then it kind of decreases in the range between 50 and 400 or 500 hertz, and then kind of goes up again. It was designed this way because this region of frequency space is where we expect a lot of the signals that we're looking for to occur. So it's quieter here because that's where the signals we're looking for are. In addition to this kind of regular noise, we also have what we call glitches, and these are a challenge for a lot of searches. There are these non-Gaussian transients that can appear very similar to CBC signals. So on the left here is the BBH signal. I almost called it a glitch. It's an actual gravitational wave signal, and then on the right is a blip glitch, and this is in time frequency space. And so this similarity can fool a lot of traditional approaches to detecting gravitational waves, as well as machine learning methods. The fact that there are signals that just come up sometimes with similar durations and similar frequency profiles. So it's something that we have to deal with, and typically, at least for machine learning, we deal with it by just throwing so much data at our network that it learns to distinguish glitches from actual signal. Great. So with this out of the way, how many gravitational wave events have we been able to detect using these detectors thus far? At this point, this is a little bit out of date. We're in the middle of the fourth observing run, 04, which has detected, I think, at least an additional 90 or so significant events. But this shows detections from the first three observing runs. So 01 and 02, when we were a little less sensitive, we found 11 events. Then in 03A and 03B, we found a lot more. So this shows there's a lot kind of going on in this diagram, but the two masses along the line are the parent objects, and then the final mass is the child object, and on the y-axis is the mass of the object in units of solar mass. So you can see that we typically detect heavier stuff. But if you look down here, we have GW 170817, which is our nomenclature for how we label gravitational wave events, which is the first binary neutron star system that we've detected, and the only multi-messenger event to date. We observed the merger of this event in the electromagnetic spectrum as well, which is kind of why I am even here to be talking at this ZTF summer school. We care about multi-messenger astrophysics, and gravitational waves are one of the messengers we get from astrophysical objects. Another is what we measure with the Zwicky Transient Facility with visible infrared light. A kind of common approach to doing multi-messenger astronomy, or at least attempting to, hasn't been all that successful, is the idea of using gravitational waves as a trigger for looking for messengers in the visible spectrum. So gravitational waves hit us on Earth, and they'll come from all directions. We can't shield our detectors from gravitational waves. That's opposed to telescopes, which are looking at a particular point on the sky and are only sensitive to where they're looking. So they could easily miss something if they're not looking in the right direction. If we can detect gravitational waves, use that information that we get from them to tell our telescopes where to point, we have a much better chance of learning more by using these multiple independent measurements as a means of constraining the parameters of the event. So why use machine learning for this task? Why do kind of the traditional methods of this approach not suffice? Speed. Speed is really crucial for doing multi-messenger astronomy well. We'd like to be able to point our telescopes at the event as soon as possible. And machine learning can be really, really fast. It can be, to kind of give a sense of some numbers, I maybe should put this in the slides, but the sort of typical follow-up time or the typical detection time for a traditional search pipeline is about 15 seconds, and with machine learning, we can be more like 3 or 4 seconds. So there's a little bit more to go on being quite as fast as we'd like, but we're already significantly faster than what the traditional methods are capable of. And this is only going to become more important. So this image is showing the sensitivities of different detectors, LIGO, Virgo, Kagra, during different observing runs, where the sensitivity is in sort of the distance that we can see out to. So higher number, farther distance. You can see that our sensitivity has been increasing over the course of these observing runs. And then in the fifth observing run, we expect to be much more sensitive than we currently are. And for reasons I won't get into, the higher sensitivity means more computation for traditional methods, which makes machine learning very advantageous in terms of computational cost and latency. So we'd really like to understand how to do this detection problem with machine learning. Okay, so if we care about multi-messenger astrophysics, we're going to focus on detecting binary neutron stars, right? Or maybe neutron star black hole mergers, because these are the things that have electromagnetic follow-up or electromagnetic emissions that we can follow up on. No, binary neutron stars are hard to detect with machine learning. We're working on it actively. We are having a tough time. We're doing a mediocre job with it right now. But for today, we'll focus on binary black hole detection. Binary black holes, as I showed in the simulated signals before, they are louder than binary neutron stars, and they have a more compact signal to noise ratio profile, the more contained in space, and those characteristics make them easier to detect. So we'll start with this. It's a good place to test out techniques that we can hopefully extend to detecting NSBH, neutron star black hole, or BNS, binary neutron star mergers. So let me introduce A-frame, which is the model that we have developed for detecting these systems. Our goal is to be able to take a segment of data, say some seconds of time series data, and label that segment as either signal or noise, and also attach some level of significance to that label. We want to say, how confident are we in assigning this label to this segment of noise? This is what's known as a binary classification problem. It is pretty common in machine learning to want to do this sort of task. You can think of labeling cats versus dogs or whatever else. So I'll go through a general overview of how A-frame accomplishes this. So I'll flash this flowchart to kind of give an idea of the path that we're going to take. We create data sets, we train the model, we test out our model, and then we do analysis on the output. So I'm not going to go too far into detail with any of this because I think that would be boring. And also you're going to be looking at this a little bit in the notebook in any case. So starting off with what data we take a look at. Up top, we have a sample of what real data from the interferometers look like. This is a stretch of 10 seconds of data from Hanford and from Livingston. Take a look at the order of magnitude of the strain. It's like 10 to the negative 19, so it's very small numbers. We take weeks and weeks of real background from Hanford and Livingston from the beginning of the third observing run to train our model to teach it what background looks like. And we also simulate on the order of 100,000 signals with parameters that are kind of typical for what we would actually expect to be out there in space. We split this data up into three different training sets, or sorry, three different data sets: training, validation, and testing. The training data set is used to teach the model what's background and what is signal. The validation data set is used to monitor the model during training. So after each training epoch, we evaluate how our model is doing on a smaller subset of data, just a quick check to say, here's how our model is doing at this point in time. And then after the model is trained, we evaluate it on the much larger testing data set to give ourselves a final metric of performance on how this model has done. A key thing is that there is no overlap between any of the data in any of these data sets. You can't validate or test on data that you've trained on. That would be cheating. Right, so once we have these data sets in hand, we can begin the training process. The general strategy is this. We're going to break our background into 1.5 second segments. I think I'm showing 1 second here. I think that's what I did in the notebook. In practice, we do 1.5 second segments. We randomly select a subset of these background segments to add these simulated signals into. And we add the last portion of a signal where it's the loudest into the background. Everything that gets injected is labeled as a 1. Everything else is labeled as 0. So signal or background. And this is, I hope, visible enough from there, but there is a kind of chirp-like signal here. So after adding signal into this background data. While we train, we monitor a couple of metrics. So we follow, of course, the training loss, and you probably encountered training loss a bit in your lesson yesterday. We also monitor our validation metric, and our validation metric is one that we want to be higher as time goes on. So this is what a healthy kind of validation curve looks like. The metric that we use is the area under the ROC curve. It's not the direct point of this lesson, but it's a pretty common metric, and it's going to be coming up in the notebook. So I'm just going to spend a slide explaining what that is, why we want it to be higher. So, right, our validation is the area under the ROC curve, or I just pronounce it ROC in my head. An ROC curve is this plot of the false positive rate of a network versus the true positive rate. If you just had a random classifier that was just randomly assigning zeros and ones stuff, you would get a straight line like this. But if you trained a model well, you will be able to have a high true positive rate while still having a low false positive rate. And that's what you want to see. You want to train your network to do that. And so our metric is the area under the ROC curve. So the closer that is to 1, the better. If we just had a random classifier that has an area of 1/2, if we had a perfect classifier, which goes up to this corner and then over, we would have an area of 1. So that's our metric. Not super important to understand all the details of it, but just something to keep in mind as you go through the training. We want this number to be higher. We want it to be above 0.5. Yes, okay. Now I'll go into sort of how we do inference, how we test out our model once it's been trained. There we go. Oops, okay. We look at overlapping segments of data to get a time series of network output. So what we do, we have this set of time series data. We take some segment of it, we pass it off to our network, and we get a single value out. Our network takes in a 1-second segment of data, and it produces a single value saying, this is what I think this segment of data is. I think it's either signal or I think it's background. And the higher that value is, the more confidently it thinks it's signal, and the lower that value is, the more confidently it thinks it's background. We do overlapping segments. So once we've done this segment, we'll step over by